as I was just saying, I don't know many people and faces, and it's interesting. It's just an opportunity for me to give a quick overview of what we are working on at the National Oceanography Centre, in particular the Marine Systems Modelling Group at Liverpool. So I've focused on a bit about transport modelling, and these are kind of applications of some of the models that we developed, and it's really a subset of what we're doing. So it's not meant to be comprehensive at all, just a quick overview, and I hope might generate some questions about what we are doing. So this is just an overview of the talk. I was going to particularly focus on what we're doing in terms of coastal modelling, coastal ocean modelling. The coastal ocean being the strip around the coast, obviously, but it's a subset of obviously the whole ocean, and we are modelling globally as well. I'm going to refer to this thing called Relocatable Nemo. Nemo is a model which is a European model which we are investing in quite heavily in developing, and this model is allowing us to explore particularly marine physics but also ecosystems to some extent as well. So our group is focusing mainly on the actual movement of the sea, the hydrodynamics, waves, other things that are going on in the sea, rather than the biology. So the biology is a bit of a closed book to me, and also the whole aspect of international law, and I'm here to learn, but I'm just going to share with you a few things that we're doing. And it's also referring here to where we get our funding from. So there's this official development assistance funding that the UK is offering nowadays, and so we have actually used that and to allow us to focus in on some issues around Caribbean and Pacific Islands. And there's also the Newton funding, which again is related to ODA, and we have projects in the Indian Ocean and in China, and then just looking at a little bit about what's going on for the Northwest European Shelf. So quickly about the National Oceanography Centre. We have two sites in Southampton and Liverpool, and the main headquarters is in Southampton. We're co-located with universities in each case, but we're not part of the university. We have 580 staff, about 100 of them are in Liverpool, and about 185 of those are science and technology staff. A lot of our core admin functions are based in Southampton, so a higher proportion of our science and technology in Liverpool relative to admin. And we have this about 45 million annual budget. We've just become a private company, but with charitable status, not-for-profit organisation, whereas previously we were a UK research institute. But we still get our funding from UK research funding from the EU. How long for? I don't know. Industry and government departments and agencies. And then we have 5 main core activity areas. So I'll just mention that marine physics and ocean climate and marine systems modelling, which is my group, or the group I'm part of, based in both sites, across the 2 sites, whereas the other 3 groups are focused in, basically centred in Southampton, but obviously we can tell you bits about both things. I'm not going to go through all this list, but it's quite important that we're providing leadership and facilities on a sort of national scale for the UK. So we have various observational and modelling efforts. We have research ships that we manage, and various other things that we're doing, like databases. We have the British Oceanographic Data Centre in Liverpool. And this is a vision which has just been articulated towards the decade of ocean sciences for sustainable development, which will begin in 2021. And I'll just pick out the one which is obviously we're looking for a healthy and resilient ocean, but what we are doing in particular is looking at predicting the ocean in the modelling group. So we're trying to understand and then hopefully as much as possible facilitate ocean prediction. There's some another activity which is based in Southampton is the autonomous vehicles, and we have a large number of gliders and also powered underwater vehicles. This is a key new development. It actually obviously avoids the need to send expensive ships to sea to some extent. And I'm just going to touch on one other activity which is observationally related before I get into the modelling side of things, which is called CAMEL. I'll tell you what CAMEL means in a second, but this is actually looking at, this is an autonomous surface vehicle tracing the Belize River plume, and CAMEL is actually a containerised autonomous marine environmental laboratory, so acronym. So, but it's actually, it's a new concept that's been derived for the Commonwealth Marine Economies projects that we've been doing, where it's allowing us to provide a modular system which can be deployed in different locations around the world, and Belize is one example of where we are deploying it. Right, so I'm just going to quickly focus on marine systems modelling and what we do. Like I say, this is the European model, nucleus of European modelling for the ocean, and it's work that we do also in collaboration with the UK Met Office. It's focused very much, the operational model of the ocean for the UK is this Nemo model. And this is how it, I wonder if this is going to, oh yes, it's going to move, great. And this is our global version of this model, which obviously can allow you to see, this is looking at the surface current speed, and you can see in particular some of the ocean current systems like the western boundary currents and things like that. So this is actually a 1/12 of a degree global model. And then we've, oh yeah, forgot about that, we got a picture of our Liverpool team in the modelling group, including 3 people who are modellers within the marine physics group as well. So yeah, there's 12 to 15 people and a similar number in Southampton. And in Liverpool we particularly focus on the coastal ocean rather than the global modelling. So we've got this relocatable Nemo model, which is actually a restricted area model which we can apply in different locations around the world. In general, the global model doesn't include tides, whereas when we deploy it on a local scale, regional scale, we include tidal forcing. And the one that I'm working on particular is the Caribbean model, so we developed a regional model. And we also have some in Southeast Asia and the Pacific and East Africa. So when we look at this again, oops, hopefully that you can see there is actually some movement here on the left hand panel. This is looking at how effectively a lot of the effects that we're seeing is the net transport from river runoff into the oceans, and then in particular this is showing surface salinity. So it is actually showing where the freshwater transport goes, which is obviously relevant for plastics coming in from rivers, for example. And some of the questions that we're asking are, how are the Pacific and Indian Oceans connected, and where does the runoff go? And the right hand is just a zoom in of the area in the black box on the left. You can obviously see that there are key rivers discharging into the ocean in these red areas. So where it may be a little bit opposite, intuitive, counterintuitive. Red is low salinity, nearly fresh water. Another example, as I say, the Belize Regional Nemo model, which is only goes down to 1 kilometre resolution, and in particular we've got sort of various tools that we've been developing in order to allow us to deploy this relocatable model quickly in any area of interest. The global news is the source of the river discharge in general, and it's been run for typically 20 years, so you can see a climatology of what is happening in a given area. I think again this might or might not, oh yes it is. So this is just to show how you can do transport modelling with that model. You can take a particular point in the model and you can see where a discharge at that location will go over time, and obviously this is an application which could be relevant to sargassum, which is a big problem in the Caribbean on the beaches, and plastics, other marine debris, etc. And we do this particle tracking, which is just going to give us some insight into where things go. It's very important then in this case that we then know about the sources and sinks of this, the behaviour of this substance, whatever it is we might be tracking. It could be oil spills, it could be, like I say, sargassum or plastics. So that is a hard bit and an area which I'm not really capable to tell you a lot about, but in principle we can apply models in this way. And this is just an example again of the Belize model, and it's using a particular particle tracking methodology with passive particles in this case driven by hourly surface currents, and you can have monthly releases over 20 years, and then you've got 4,000 particles per release. And this is just a sort of bottom right is like some of the tracks that are taken by these particles. This in this case is looking at where things coming offshore are finishing up, but it can be onshore coming offshore as well. I'm just quickly mentioning as I pass one of my other projects, which is about transport in the South China Sea related to the Pearl River Delta, and we're looking at in particular the effect of natural coastal defences, i.e. planting mangroves in this very urbanised environment, and we're looking at how that could be carried out. It's actually a joint China, UK, Netherlands research project, and we're modelling this area because it is a key, really one of the most urbanised areas in the world with high population and also very vulnerable to coastal flooding. And then we set up a different type of model called FECOM, which is it's based on an unstructured mesh because it allows you to do a higher resolution in the very narrow channels that you want to explore, whereas you're also keeping coarse resolution offshore. We have a couple of projects which are on the northwest European shelf, and one example is here about the connectivity of oil and gas platforms. This is looking at how different species might use these as artificial reefs effectively, and how that enables different species to behave in a different way. So there is a suggestion that every object in the sea should be taken away, but a secondary consideration might be the benefits that species are taking from these things. So at least the first step is to try and understand how these reefs, if you like, are these old oil rigs which have been truncated in some cases, but they still exist underwater, how they are facilitating species interconnectivity. And finally, a project that again is one of my projects is looking at our Northwest European shelf FECOM model and particle tracking for sea lice larvae in farm management areas. So the question was how these farm management areas in Scottish waters are connected. And again, we can look at running a model of the hydrodynamics and then saying where do things go. And this is just an 8-day run of the model of tracking particles over 8 days in January, and a zoom in of that. So I had, I think, 20 minutes, just wanted to touch on these things. I don't know how much interest there is in knowing more about it, but if you want to know more, please come talk to me or come and visit us, because we're only in Brownlow Street around the corner, next door to the Earth and Ocean Sciences Department, basically. We collaborate with already. So, thank you.
Questions? I actually have some. The Relocatable Nemo is a model.
Yes.
The EMO is the European.
It's the nucleus. It's NEMO stands for the nucleus of European modelling of the oceans. So the nucleus, N for nucleus. Don't ask me where they got that name.
So what is this? It's a mathematical model, right?
Yeah, sorry, I didn't really go into the background of what is a model. You know, that could be another lecture. But obviously what we're doing is we're dividing up the ocean into boxes and solving the equations of motion in each box.
Okay.
And that allows us to, at different resolutions, understand what processes are driving the transport in the ocean.
So this model is written in a computer language?
Yes, it's written in Fortran.
In Fortran, of course. And so some of these, like, and some of the plastic has sort of effectively sails on it. And then
Yes.
you have 32 vertical levels.
Yes.
So that's, I'm familiar with hydrodynamical models on the land, but that's we follow where the water goes.
Mhm.
You're following where the water is going, right? Because of
Yes, effectively, but yes.
currents and you're keeping track of.
Yeah, so the
Right.
flow in the ocean could be driven by tides, by winds, some of it mediated through waves. We've got wave models which then calculate Stokes drift, as was mentioned before, and things like that. So we have all those different processes accounted for, and we can then say where the water particles are going,
Right.
and then if you put in some particles into that, you can track them around following the ocean currents. But also, it's also including dispersion of these particles, either mixing in the vertical or in the horizontal. So I'm not giving any of the background of that, which is a separate area in itself, obviously. And then we validate these models against both remote sensing data or observational data, and that's our kind of expertise, if you like. And then there's the applications, which could be to such things as the transport that's required a part of plastics in the ocean. So we are looking to, we are carrying out a certain amount of work on plastic in the ocean, and as usual you have to find the funding in order to do that piece of work, so finding appropriate researchers.
So you do have
research
surficial wind effects.
Yeah.
My big complaint about these hydrological models on land is that they say they're deterministic models. Is your model deterministic as well?
Oh yes. It's solving the equation of motion. Having said that, we are addressing uncertainty in terms of running an ensemble of models, various.
Ensembles.
Yes, so we run ensembles. There's more behind it than just purely deterministic modelling, I suppose you could say. So we do have to address probabilities. Pardon? I didn't catch the.
No. Go on.
Were you laughing at me?
Yeah.
I assume, yes. But so let me get this straight. So it is a deterministic model, but you might run it in a shell that runs at any time. Is that what you meant by there's more than...
And particularly for the particle tracking, where that is trying to represent some much smaller particles by a kind of behaviour of a number of particles, you have to seed the ocean model with particles which represent in some way the behaviour of the real substance. And in general, that's often done by doing several experiments, many experiments, repeating experiments in order to see where the particular turbulence and some process of mixing in the ocean is still very, it's kind of empirical, so we're still
I thought you
tuning.
were going to say dark art.
Yeah, don't.
Yeah.
I'd say that as well. We don't like black box,
No,
but
like that.
it's to some extent there is that.
But to run it with what if wind is an input, that means you're not predicting the weather, obviously. So that's a.
In
That's
general,
an input
no,
that
we're
you're
using other people's atmospheric modelling to force our models in. We use the Met Office, but also ECMWF models, and there are other models out there. So we can also.
Presumably you could use a stochastic.
Yeah.
Doesn't predict a single kind of wind.
Well, exactly. So for the UK Met Office has an ensemble where they're running that every day to predict the behaviour of storm surges, for example. How likely is a storm to hit a given part of the UK? There is a certain amount of probability built into that.
So I assume it depends on the size of your relocatable area, but what kind of computation times are we talking?
Well, we are talking about using high performance computing, basically. So, how long's a piece of string?
In those platforms, are you routinely do week-long simulations or
we run both on event scales of like hindcasting a storm event to climate scales where we're looking at thousands of years.
Yeah.
And obviously once you start running thousands of years you have less opportunity to do ensemble modelling. So yeah, trade-off.
Right. Okay, thanks. That's very helpful.
I'm not sure that I have a very well formulated question here. If you're doing something like Nemo with reference to an object floating in the middle of the ocean like an ocean, would you fix the frame of reference relative to that, or would you have everything moving relative to a fixed point of reference on the world?
Well, we're generally running what are called Eulerian models, where it's a fixed frame of reference relative to the globe for our ocean circulation. But then, I don't know whether you noticed the word Lagrangian popping up on the particle tracking, so then you're following the particle as it moves through the field of ocean currents, for example. So you have to, trying to account for the behaviour of the particle in terms of its moving through an uncertain field of currents is complicated. Sure, that's an answer. But we do both, in other words.
What was the question?
Whether you're moving with the frame of reference of the particle or the currents.
Or Larian
Or absolute.
question.
Well, the question was really, if you've got a floating object of interest, like a do you fix the frame with respect to that? Fix it with respect to sex.
Okay, yeah. So
I have a whole lot of questions. Thanks for the very nice overview. And obviously, Lagrangian transport modeling is our main tool also to assess what we discussed this morning. So we'll try to find you later. But quickly to your question, we, for instance, do both. We assess in a global reference scale global plastic dispersion, and on a local scale, indeed, in a fixed reference frame, some mechanisms around our system, where we then nest it in a global, for instance, a swan model is a wave model. I don't know if you
Yeah, we use the Swan model and WaveWatch 3 as well, for different scales.
So in the first step, our 60 systems, would be Lagrangian tracers by themselves with certain properties, and then along those trajectories we extract the ocean conditions that then force a local model in a local system reference. So we're doing both. For you, my question was, so I saw also quite some measurement equipment, and you said validation yourself.
Yes.
That, I guess, for us is actually the biggest challenge at the moment, the validation of the transport model. So at a global scale, we're doing that by running Lagrangian models over long periods of time, and then basically translating that into doing like an Eulerian mapping of surface concentrations of plastic, for instance, that would translate to, which then can be compared with the results of the mega expedition, for instance.
Yeah.
So, and that's also what other research groups do, and for like global scale that seems to be doing a good job. But now zooming into the system, how then at a very small temporal and spatial scale plastic behaves compared to Houston, for instance. The sensitivity of Lagrangian models. Do you have any advices there in terms of validation?
Well, yes. You get into the nitty-gritty, the real challenge. I don't know whether, to be honest, I'd never heard of Houston 2 weeks ago, so I was reading up on what was Houston. I don't know how you observe Houston, and I don't really know enough about how much we know about this particular stuff in the sea. So we've been working with either remote sensing data where you can see a patch of a substance, a certain amount of drifter kind of experiments, oil slick modelling, specific, like released drifters, or the Argo floats, or any of these things which allow you to try and challenge the model against data. again, no model's ever going to be perfect, so we're going to try and keep on improving the model interface with data and gathering as much data as possible to challenge a model against. I don't know whether we probably should have a conversation specifically about, are there any questions that you find your models are challenged by, or are we all using the same models? Are we using the same types of models? And how much effort do you have to put in to get a model that you trust? And specifically again for plastics, how much do you need to know about how plastics behave in the sea, which types of plastics, etc. So I would say I haven't any experience of modelling plastics. Some people are trying to use the models for modelling plastics, but at this stage it's only been at the level of assuming this is a completely neutral particle. So we need to know about how the plastic sinks in the sea, how it's consumed, or how it interacts biochemically with what's going on. I think one question would be, how much is it large plastic objects that we're talking about, or how much are the plastics turning into very small particles and then being consumed? Is that the more important part of the problem? Is just capturing the big stuff enough? There's so many questions about the application, which I've got to admit, I'm just coming here to learn about what you're doing. So, do you have any feedback for us on what the challenges are for the modelling that you're doing?
Well, trying to put that now into 3 sentences. So we're trying to address most of what you just mentioned, for instance, running then different scenarios with different types of plastics, and also assuming different evolution or degradation of the plastic. So for so many years it's forced at that size, and then it breaks down and so on and so forth. We're only just starting to go into 3D modeling, so not only assume a vertical mixing due to sea state and then a current at different levels, but actually look at do a full 3D model.
Mm-hmm.
But we can do a lot of modeling, and also when it comes to the forcing of the particles, so the current, stochastic and wind contribution, and what are those? It's like 3 major factors that you need to choose as a modeler, and you also mentioned you then end up running scenarios and analyzing it in a stochastic way. What is your sensitivity to those parameters? But that appears to be huge.
Yeah.
And that appears to be manageable for a global scale, again, where there seems to be quite some confidence in the different worlds now that we have those plastic concentration areas, so at a basic scale that kind of works. But when it really comes to zooming into how does now a system move relatively to which type of plastic, and then also compared to Newton, for instance, that appears to be a whole other challenge. And how to translate, for instance, what we can do in a lab, like we do Bayesian experiments with different pieces of plastic, expose it to different currents and waves, then the whole scaling question comes in there. No one really knows how to scale plastic and how to then translate those findings into model parameters. So more questions than answers.
I'm quite encouraged by that. We don't want to think it's all done already.
Do you I know nothing about any of this area, of course, but Akira Kubo used to tell me that about this story. Maybe it's apocryphal, maybe it's not true at all. About this plant. There's this big project in the early 1980s in which they manufactured 1 billion of these little plastic balls, apparently with labeling on them. They were put them into the ocean and then watch where they went, and they had this grand scheme of receptors, scientists all over the planet who were going to watch them, because they were interested in the ocean currents, right? It was when we were studying that. It was before remote sensing got quite as good. And they manufactured these plastic balls, and they put them into the ocean streams, and they never saw a single one of them again. You know this? Is that a true story? You've heard it too?
Yeah.
Well, my cousin's uncle knows somebody that did that.
They did it with the plastic ducks. That was really
So that was
accidental.
accidental.
And there's a study at Oldenburg University in Germany
indeed, that's right. Yeah.
And probably
In the past, we have done dye experiments, but it's it is a bit sort of debatable how ethical it is to introduce anything into the sea.
Judith, you've gone infinite.
I just pulled this out because I thought you might have run out. I might have run out of time.
there is in oils, there are some models for oil spills, so maybe probably you're already using data from oil, maybe seeing which kind of plastic behaves like crude oil. And the crude oil, the oil companies, sometimes when they want to model a spill, depending on the oil, once they go in the surface, they throw popcorn. So Norway usually throw popcorn because the regulator agreed with that. So that's a problem about the regulator.
Yeah.
Yeah.